So we'll prove our first proposition, which is that if M is a substructure of N, which I write this way, now this hides some complexity, by the way. Let me get into this before stating the rest of the proposition. And it does involve something that I neglected to mention in the previous video. M is a substructure of N if, yes, the domain of M is a subset of the domain of N, and there is this L embedding, but there is this subtle language that I sort of glossed over, which is that also the mapping that we must use in this case to call it a substructure is in fact what's called the inclusion mapping, which is basically the identity mapping on M into N. So in fact, when we map any given element, it must map to itself. So that is part of the assumption in this proposition. So if we suppose that we have a substructure, which, again, the domain is a subset, and we use the inclusion mapping from M to N. If we also assume that we take a vector of elements out of M, and this also deserves some comment because, after all, this is an M-length vector, each element being selected out of the domain M, so this notation actually doesn't make sense, but it is an intentional abuse of notation, just as the author of the book uses, which is really just shorthand for specifying the number of products that we should be taking of the domain with itself. So, okay, we have this vector of elements out of the domain, and we have a same length vector of free variables in this formula phi. And phi is quantifier free. Then we get to state the following, that the structure M satisfies phi, the sentence phi of A bar, if and only if the structure N does. Now the proof of this is tedious. It splinters into all of these different cases. 2 of them are base cases, the rest are inductive cases. I will probably not prove all of the inductive cases because they all kind of go the same way, so I'll just prove one of them. And before getting into the base cases, we prove this lemma, which is that for any individual term, it maps in M to the same thing that it maps to in N. This is also proved inductively, with base cases being the constant and variable terms, and the inductive case being the case of a function built out of other terms. Now, because we're using the inclusion mapping then, right, that was important, we know that the denotation of C and M is, in fact, equal to the inclusion mapping, because after all, the inclusion just is the identity map, so it maps to itself, and that this, by definition of it being an L embedding, is also equal to the denotation in the structure N. So that establishes this case of the constants. A similar argument, which is not hard to follow, goes here for the case of variables, and then we go by proof by induction for the case of a function f. Now, that goes by saying, suppose we have an n-ary function with, again, I should probably have n sub f there, the appropriate number of terms to feed into the function f. We know that the terms do the right mapping, so if we take the restriction of the function, we get this chain of equalities. It's all fairly common sense, so I won't waste more breath on it, but I will continue the proof in the next video.